Atoms are made up of three separate particles: protons, neutrons, and electrons. Protons carry a positive charge, while electrons carry a negative charge. The charge is measured with a unit called the coulomb. Protons and neutrons make up the nucleus of the atom, while electrons orbit the nucleus in a manner analogous to the planets of the solar system orbiting the Sun, and with the attraction between the opposite charges of the electrons and the protons analogous to gravity that maintains the planets in orbit. Electrons occupy defined orbital shells, with a limited number of electrons permitted in each shell. The total number of electrons per atom is unique to each element. The outermost shell is called the valence shell. Electrical conductivity is defined by the movement of valence shell electrons between neighbouring atoms. For electrical conductivity, valence shell electrons must be free to leave the atom. This can only occur if valence shell electrons can reach something called the conduction band. The conduction band can be thought of as a gate to leave the atom. For conductors, including all metals, the valence shell is fully overlapped by the conduction band, or alternatively, is partially overlapped by the conduction band. In both cases, valence shell electrons are able to access the conduction band and so are free to leave the atom. For insulators, the valence shell is far from the conduction band, and so valence shell electrons are unable to access the conduction band and are not free to leave the atom. For semiconductors, the valence shell is close to the conduction band. Under normal conditions, valence shell electrons are unable to access the conduction band and so are not free to leave the atom. But if external energy is provided, valence shell electrons can jump the gap to the conduction band and so are then free to leave the atom. The guaranteed free movement of valence shell electrons between neighbouring atoms is what makes metals, such as copper, ideal materials for electrical wiring. Meanwhile, the guaranteed blockage to valence shell electron movement is what makes non-metals, such as plastics, ideal insulating materials so we can handle the wiring without being electrocuted. Let's take a look inside the piece of electrical wiring. Inside the metallic wire, the valence shell electrons are free to leave their atoms and move around the material. We call these electrons free electrons. Usually, the movement of free electrons is random, as they float around without any particular direction, a bit like a ship lost at sea. However, if we have a forced flow of electrons, for example from a battery, the free electrons start flowing in that direction, a bit like a ship flowing with the current at sea. Indeed, current is an appropriate word. This flow of free electrons in a specific direction is called electric current. Current is measured as the electron flow rate and has the units of amps. 1 amp is equal to 1 coulomb. 1 coulomb equals 6.2 times 10 to the 18 electrons per second. The force that pushes the electrons is called voltage. Voltage is measured as the force or pressure required to push a specific amount of electrical energy and has the units of volts. 1 volt is the force required to push 1 coulomb, that's 6.2 times 10 to the 18 electrons, through a resistance of 1 ohm in 1 second. So what is resistance? All materials present some resistance to electron flow, or current. Resistance occurs as the free electrons crash into the atoms. For highly conductive materials, this resistance is lower, whereas for less conductive materials, it is much higher. Also, electrical devices that are powered by the current create some resistance. The resistance is what causes old-fashioned incandescent lamps to light up. As the electrons struggle to flow through the filament, crashing into the atoms of the filament, some of that kinetic energy of the moving electrons is transferred into light and heat. Electrical resistance is therefore the opposition posed to current and has the units of ohms. 1 ohm is equal to the resistance exerted against a current of 1 amp when a voltage of 1 volt is applied to it. Current, voltage and resistance are related by Ohm's law. Current is equal to voltage divided by the resistance. Power is the rate at which work is done. Specifically in terms of electrical power, it is the rate at which electrical energy is transferred from our power supply, such as our battery, to our circuit. Electrical power can be calculated as current multiplied by the voltage and has the units of watts, where 1 watt is equal to 1 joule of energy per second. Energy is then the amount of work performed, and 1 joule is equal to the heat dissipated when an electric current of 1 amp passes through a resistance of 1 ohm in 1 second. To put this into some sort of context, let's say we have a 1.5 volt battery and a 1 watt rated lamp. In order to keep the lamp lit, we need to pass 1 joule of energy through the lamp every second. The current required is going to be equal to the power divided by the voltage, which is 0.67 amps. The resistance is given by rearranging Ohm's law. Voltage divided by current, which is 2.25 ohms. We already know electric current is the flow of free electrons in a specific direction. However, there are two types of electric current: direct current, DC, and alternating current, AC. With direct current, the electrons travel in just one direction. This is a bit like the flow of water along a river, where water flows in just one direction. Electrons, which carry a negative charge, flow from the negative terminal to the positive terminal of the power supply. Electrons are repelled by the same charge of the negative terminal and are attracted by the opposite charge of the positive terminal. Direct current is produced from batteries and is used to power almost all of our small portable devices, such as laptops, smartphones, and tablets. Direct current is also produced from 12-volt lead-acid car batteries found in internal combustion engines, where it is used to power the various electric water, oil, and fuel pumps throughout the engine, in addition to the air conditioning, entertainment system, and window wipers and so on inside the cabin. Direct current is also produced from the vast battery packs that are integral to hybrid and electric vehicles. With alternating current, the electrons travel back and forth. This is a bit like the flow of the tide at sea, where the tide repeatedly comes in and out. Alternating current can be generated by constantly reversing the terminals of our power supply. In practice, however, this is done by a rotating magnetic field. Alternating current is the most common type of electricity and is found in our plug sockets to power our homes. Alternating current is also produced by the alternator found in engines. In almost all hybrid and electric vehicles, the motor generator unit, MGU, uses alternating current in motor mode and produces alternating current in generator mode.